All right, here we go with example 6. We're talking about inverses. It says if f of x equals 4x minus 2, determine if f of x is 1 to 1. If it is, sketch the graph of it, and then graphically and algebraically find f inverse. Okay. How are we going to determine if it's 1 to 1? Well, there you go. Yeah, a function we said yesterday is 1 to 1 and therefore invertible if it passes both the vertical and the horizontal line test. Okay? So what do we know about the graph of 4x minus 2? It should graph as a what? A line. And is the line going to pass the horizontal line test as well as the vertical? Yeah, it should. So there's -2. That's the y-intercept. So there's my first point. And then if you just want to find out what the value at 1 is going to be, what would be the y value at 1? Should be +2, right? If you plug in a 1. So I will draw that in purple nurple. And I'm going to call that f of x. So I'm going to label the graph. Now you can easily tell from the graph that it does pass both the vertical and the horizontal line test. Ergo, it is 1 to 1, and it is invertible. The horizontal line test means if you slide your forearm from low to high horizontally, if the graph touches your forearm more than once, it's not going to be 1 to 1. Okay, just like the vertical line test, if it touches, it's not a function. So what that means then, if it's 1 to 1, remember, is every input only has one output, and every output comes uniquely from just one input. Yeah, it's that 1 to 1 happy romantic relationship. The x's and the y's are faithful both ways to each other. And because it's 1 to 1, we know that it's going to have an inverse that is a function. Okay, so let's go ahead and get the graph. To get the graph of the inverse, all we have to do is reflect this graph across what magical line? Not the y-axis. Y equals x, right? And I showed you all that yesterday with my low-tech paper, right? I was flipping it. I held my hands in place, and I didn't move them. And remember, the landscape became portrait, and portrait became landscape. So there's the mirror across which we'll reflect it. Now, you could get a couple of points. Let's choose, what's a good complementary color to purple? Green, okay. You can actually get a couple of points on the inverse. If the function f has a y-intercept at 0, -2, then what would be the corresponding point on the inverse? -2, 0. Good. Remember, we call those corresponding points. So there's -2, 0. The y-intercept of f is going to be the x-intercept of the inverse. And we call those, again, what kind of points? 0, -2, and -2, 0? Corresponding points. We plotted another point on the function f at 1, 2. What would be the corresponding point on the inverse? 2, 1. So if you want to come out here to 2, 1, it would be right about maybe there. Now you only, what's that? Every point on f is going to have a corresponding point on its inverse. That's kind of what the 1 to 1 means. We have a corresponding point, and they correspond 1 to 1. So what you can do is just get a couple of points. That's all you need for a line. And then take the corresponding points, interchange x and y, and plot those new ones. And now you can connect the two dots with a straight line. And of course, you notice then that those two graphs, the purple and the green, they look symmetrical across that dotted yellow line that I drew, right? Okay. And the corresponding points, if you want to kind of line them up, like this point right here, whatever it is, if you come straight across here, and I know it's not drawn perfectly to scale, if you come at a right angle to that line y equals x, that corresponding point is going to be over there. Okay, so it's almost like turning your iPad 45 degrees and looking at the dotted line like a vertical line. Oops. They're going to be corresponding straight across perpendicularly. So like this point up here, whatever it is, if you draw a line perpendicular to that line y equals x, you're going to get the corresponding point over here. So in general, what I'm saying is like this point A, comma B, is going to correspond to this point over here, B, comma A. Make sense? X-intercepts of one become y-intercepts of the other. The domain of one becomes the range of the other. Okay, so I'm going to get rid of all that. That was not illegal, but it does kind of obscure the graph a little bit. What do you notice about the slopes of those two lines? Are they both positive? Or is one positive and one negative? They're both positive, okay? One is steeper than the other. Now, we saw the relation yesterday that when we had the other line, that the inverse ended up having a slope that was related how to the original? Remember? They weren't opposite reciprocals. They were just reciprocals, yeah. So if the slope of our function f is what? What's the slope of our function f? 4. What should the slope of the green one be? Should be 1/4, and that's pretty reasonable. Okay, so let's go ahead and find the equation. We know how to find the graph, right? We reflect it across the line y equals x. We know how to find corresponding points. We just literally interchange the x and y coordinates, and now we're ready to find the equation. And you've done this before in Algebra 2. The first step is to call f of x, y. We're going to find the equation of the inverse function. F of x is just a fancy name for y. Here's the magical step. You're going to interchange x and y. You can do it for finding individual corresponding points. 0, -2 became -2, 0. But if you do it with x and y, you're doing it for all points. So there's the magical step. X equals 4y minus 2. Now all you have to do is resolve for y. And when you resolve for y, what you end up doing algebraically, like you learned in Algebra 1, you end up doing the inverse operations in the reverse order. So that's how we did it yesterday intuitively. So if I add 2 to both sides, I get that. Now instead of dividing both sides by 4, I'm going to go ahead and multiply both sides by 1/4. That'll serve the same purpose. So I end up with, over here on the right, I end up with y. And if I distribute, I get 1/4 x plus 2/4, which is 1/2.
Well, what happens if you divide by 4?
If you divide by 4?
Oh, yeah.
Same thing.
Oh.
Yeah. Well, why would I do it this way? Well, let me show you. If you divide by 4, no big deal. You're going to get y equals x plus 2/4, which is fine. But to get it back into a linear format, mx plus b, you would then have to split it up, right? Y equals x/4 plus 2/4, and then simplify that, and guess what you're going to get? You're going to get 1/4 x plus 1/2. So it's the same thing. Now, of course, we recognize that as a linear function, and so now we can change y to f inverse, and we'll call it 1/4 x plus 1/2. And that is the equation then of that green line. And notice the slope is in fact what? Positive. But it's also the what of the original slope? It's also the reciprocal. Yeah. So inverse functions have reciprocal slopes. That's kind of an important calculus topic that we'll get to later. Okay, what else can we do? Well, we can answer the rest of the questions. We can find f of 2. All right, let's find f of 2. How do we find f of 2? Plug in 2 for x, right. And notation is everything at this level, so we'll say f of 2 equals 4 times 2 minus 2. That ends up being 8 minus 2, which is 6. Now, the beauty of function notation is when you say f of 2 equals 6, you actually are giving another version of an ordered pair, 2, 6, that exists on the graph, right? That's the beauty of function notation. Now, if 2, 6 is a point on the function f, then the inverse function f inverse should have a point on it that corresponds to 2, 6 called what? 6, 2. Right? That would be the corresponding point. Well, we're going to verify that because now it says to find f inverse of 6. And of course, f inverse of 6 should equal 2. Let's see if it works. We'll plug that into our f inverse function, and we get 1/4 times 6 plus 1/2. And if we simplify that, we get 6/4, which is also known as 3/2, plus 1/2. That's common denominators there. 3/2 plus 1/2, that's 4/2, or 2. Yay. So what did we just do? We just verified the corresponding point. And it works for all points. Every single point on f is going to have a unique correspondence with a corresponding point on f inverse. And it's a 1-to-1 correspondence. They line up perfectly. Okay. We did it for 2 and we did it for 6. We did it for the point 2, 6. Is there a way to do it quickly for all values of x? Well, What did we do in the very beginning of this section? We looked at the elephant blanket. You remember the elephant blanket? And I showed y'all that if we took the percentage discount versus the $10 off discount, it would not be the same price if we did it either way. And I turned it into composition. So the moral of this story was that composition of functions in general is not commutative, is it? F of g of x in general is not equal to g of f of x. But it is in certain circumstances. Let's try this right here. Let's try f of f inverse of x. Let me switch to a thinner writing utensil. That's f of f inverse. That's composing them. What do you think we should end up with? Any guesses? If you compose a function with its inverse? 0, 1. Good guess. Let's see. Let's start from the outside. My function f is 4 input minus 2. 4 input minus 2. And what am I plugging in the parentheses? The inverse function, which we just found to be a fourth of x plus a half. Okie dokie. So I'm going to plug in there 1/4 of x plus 1/2. Let's go ahead and simplify that. If I distribute the 4, I get 4/4, also known as 1, so that's x, plus 4/2 is 2. Minus the 2 that's outside, I get what? X. Holy moly. I ended up with x. That's weird. Hey, let's try it the other way around, y'all too. Let's try f inverse of f of x. Let's try composing it the other way. In general, is composition commutative? No. So in general, would you expect to get the same thing? No. Let's see what happens here. Now my outer function is 1/4 x plus 1/2. So it's going to be 1/4 parentheses. And what are we plugging into the parentheses? F of x, which is 4x minus 2. Let's go ahead and simplify. If we distribute, a fourth of 4? 1. So we're left with x. Minus 1/4 times 2? 2/4 or 1/2. Plus the 1/2 that's out there, what happens with your 1/2s? They add together to give you a 0 pair, and we're left with just x. Whoa! Holy moly smokers. They're both equal to what? X. So apparently, composition is commutative when the two functions you're composing are what? Inverses. Is that surprising to you? It shouldn't be, because notice what we're doing. If you look at the order of operations, you're starting with what as your independent variable? X, okay? So I'm going to stand right here. X marks the spot. You see me? Here I am. If you actually look, the tiles intersect on the ground to make an X. I'm going to stand on that X, okay? Now I'm going to apply the F inverse function, and let's say it takes me over here. Here I am. I'm at F inverse. Now what am I going to do? I'm going to apply F to that, which should undo F inverse, right? That's what inverse functions do. They undo. So if one function takes me 2 steps to y'all's right, the inverse should take me 2 steps back to my left, and guess where I'm at? I'm right where I started, at X, right? I started at X, I ended at X. Does it matter the order? What if I first take 2 steps to y'all's left? Now I'm over here. Hello, everybody. Now I undo that, I apply the inverse, which would be 2 steps back to my right. Guess where I'm at? Same place, X. So, if you start with an X, and you apply 2 inverse functions back to back, you're going to be right back where you started, which is at what? X. So not only if inverse functions are composed will it be commutative, but you'll always get what? X. You'll always get X each and every time. This gives you a way to test for inverse functions. If I just hand you 2 functions, call them f of x and g of x, and I wanted to know if they were inverse functions, if you compose them both ways, and each time you not only get the same answer, but you get x each time, they're inverse functions, because it's the only time composition is commutative. Pretty sweet. Okay, and the other thing, again, we want to make note of is the slopes of these functions are related how for inverses? Inverse functions have slopes that are reciprocals, not opposite reciprocals. Opposite reciprocal are perpendicular slopes. These are just reciprocals. Okay, number 7. Let g of x be the inverse of this. Okay, no objections from me. I'll let it happen. This time only. Find g of f, and f of g. Find g of f, and f of g. Okay, okay. How are we going to find g if g is the inverse of this? Yeah. Replace f of x with y. And then, of course, the magical step is to interchange x and y. Now, you could skip the first step, right? If you know f of x is just a fancy name for y, you can go right to the purple step. But you are going to interchange it. And we know why this works now. We saw it graphically, corresponding points. We saw it individually. We saw it for the whole graph. And now all we have to do is solve for y, which means we're peeling back the layers algebraically, doing the inverse operations in the reverse order. So how would you start peeling back the layers to get back at y? What would you do first?
Add 5.
You would add 5, because the original function, the last thing you did was subtract 5. The first thing you're doing on the inverse is subtracting, or adding 5. So you get that. What would you do next? Divide by -2. Now, if you divide by -2, we'll do it like this, and we'll clean it up later. You get that. And now, how would you uncube root something? Don't cube root it again, but cube it, okay? So if you cube it, apparently Noah's Ark was so many cubits long. Different cubit, I believe. Was it 300 cubits? You get that, and now all you have to do to solve for y is add 1 to both sides. So we end up with this wonderful thing, x plus 5 over -2 cubed, and then plus 1. Now, is that a function? How do you know? It does have an x in it, but we've studied this before. How do we know if it's a function or not? It's solved, first of all, explicitly for y in terms of x. That's good. And remember, we said from the equation, the powers on the y's tell you how many general solutions you have for each x value. And because we're able to solve it for y to the first, that means that every x is only going to have one y value. So this is, in fact, a function. We know that without having to graph it. So we can give it the exclusive name g of x. Remember, g of x was defined in the beginning to be f inverse. We typically do that because f inverse is a little bit of a cumbersome notation. So if we just define it to be some other name, we give it a nickname like g, that's good. Now let's go ahead and clean this up. That's the same as x plus 5 cubed all over -2 cubed. Would you agree or disagree? These are properties of exponents. Now in the denominator, what is -2 cubed? -8. Dividing by -8 is the same as multiplying by -1/8, right? So I can write it like this, which is going to be a little bit nicer because this is actually in what kind of form? Standard transformation form. Sweet. So notice that we started with a cube root function, and it was also in standard transformation form. Notice if you look at the shifts, it picks the cube root function up and moves it what? The -1 moves it right 1, and the -5 moves it down 5. So right 1 and down 5. What would be the inverse of down 1 and right 5? Left 5 up 1? That's exactly what we did down here on the cubic, right? We went left 5 up 1. We did it on the different axes too, okay? So instead of going down 5, it would be up 5, but when we put that on the positive x-axis, it's the other way. So is it reasonable then that the cube root function and a cube function are inverses of each other? You cube a number you didn't mean to, how do you get it back? Cube root it, and versa versa. Now we can't talk about the slopes being reciprocals here because these graphs are curved, right? And the slopes change everywhere. But you'll see in calculus that at corresponding points, the slopes are still reciprocals of each other. All right, let's do one thing before we go to part B, because this is just part A. Let's go ahead and find f of 0. I'm kind of curious. That would be the what of the graph of f? The y-intercept. What do you get when you plug in a 0? The cube root of -1 is what? negative 1 to the 1/3. Is that what you're going to say? Which is what? Negative 1. Right. Remember, the cube root of negative 1 is negative 1 because negative 1 times negative 1 times negative 1 is negative 1. So this ends up being a negative 1 times the negative 2 gives you positive 2, and then 2 minus 5 is negative 3. So if the y-intercept of f is negative 3, that should be the what intercept of its inverse g? X-intercept. So the corresponding point, if f of 0 equals negative 3, then g of negative 3 should equal what? 0. Yeah, and we have the point negative 3, 0, the x-intercept, corresponding to the point 0, negative 3. Let us verify. Okay, let us verify. G of negative 3. Let's come down here. G of negative 3. We're expecting to get 0, right? Let's see if we do. Negative 3 plus 5? What kind of 2? Positive 2. 2 cubed? 8. 8 times negative 1/8? Oh. Negative 1, right? And then negative 1 plus 1? 0. Nice. Nice. So what we just did is we verified that the x and y's correspond for a particular single point. Okay? What we're going to do now is verify that they correspond for all of the points. We're going to compose them back to back. Are you ready? G of f of x. G of f of x. Boy, that's the same as g of f of x written like this. Yes, yes? Yes, yes. And that's kind of easier to understand. So that's the workable format versus the condensed. So we're starting with the outside function g, which we just found. It's going to be negative 1/8, parenthesis, input plus 5, cubed plus 1. Everyone see what I did? On my g of x function, I replaced x with what first? Parentheses. This is to help me substitute one in for the other. Now, in the parentheses, where x used to be, I'm going to put f of x, which is this wonderful, wonderful thing right here. Negative 2 cube root of x minus 1 minus 5. Oh, my gosh, that looks drastic. Can we do this? The answer is, of course we can. Inch by inch, it's a cinch. So your order of operations, parentheses first. Those parentheses now that I have right here and right here, they were super useful for plugging in. I can see that I'm actually getting a placeholder for some quantity that I plugged in for x. But there's really no reason to have them anymore because there's nothing to distribute inside of them. So now they're getting in the way. So if they were gone, you would be able to combine the negative 5 and 5. Do y'all see that? And what would happen to the negative 5 and 5? They would cancel to give you 0, and we'd be left with negative 2 times the cube root of x minus 1. So I'm not going to do too many things in one step because I don't want to make careless mistakes. Now the negative 1/8 is still hanging out front. Remember now I have two factors essentially, a negative 2 times a cube root of blob raised to the third power. Because they're multiplied, because they're factors, not terms, I can cube each factor, right? Remember that? Back in the day, like day 1, day 2? So what would negative 2 cubed become? Negative 8 times. What would the cube root of x minus 1 cubed become? X minus 1. Now if I write it like this, how am I doing? If I write my x minus 1 like that, how am I doing? Bad. Why? I don't have parentheses around it. Good. Parentheses are your best friends in this class, right? Better to have them and not need them than need them and not have them. Okay, now I have two options from here. I can either distribute the negative 8 in, or I can just multiply those two factors together. What would you like to do? Yeah, I would multiply those two factors because at this point, you have the associative property. You have a negative 1/8 times a negative 8 times an x plus 1, and then this could be gone, and then it's just plus 1 at the end. So it's always nice to kind of reprioritize and think which ones make sense. Although it would work either way. What is negative 1/8 times negative 8, though? Positive 1, which is nice because then there's nothing to distribute. So we can just drop those parentheses around the x minus 1, and of course we get x. Yowza. Were we expecting x? Yes, because the two functions f and g that we composed are related how? They're inverses of each other. Yep. Guess what's going to happen if we do f of g? We're going to get x. All right. Do you want to show that? I might skip that and leave that as an exercise. It would work very similarly. So here's the theorem for inverses. Two functions, f of x and g of x, are inverses of each other if and only if f of g of x equals g of f of x. Now the if and only if means it's bidirectional. If you know you have two inverses, then this is true. But it works the other way around. If you do this and you see that it's true, then you know that the two functions you composed are inverses of each other. Very, very important. All right, this is going to be example 8. This is going to be like one on your quiz. Are you ready? You're going to have one like this on your quiz tomorrow. Let h be the inverse of this function. Let's find the inverse. How are we going to find the inverse? Yeah, you could do that first step. Replace g of x with y. That's an easy first step. But then the money step, which I'll use green for, is to do what? Yeah, interchange x and y. So x equals 2y minus 1 all over 4y plus 3. Huh? Now all I got to do is solve for y. So let me show you the algebra involved here. If you multiply both sides by 4y plus 3, you're going to get 4y plus 3 times x on the left, and it'll divide out, giving you 2y minus 1 on the right. You'll see that? It's like x over 1, so you can think about it as cross-multiplying also. Yeah, I got rid of the denominator here. I multiplied both sides by 4y plus 3. It divided out over here, and I picked it up on the left. Everyone okay with that? I didn't show that on this line. I just did it. Now from here, in order to get your y's together, the math is always the same. You got to distribute. So you get 4xy plus 3x equals 2y minus 1. Now because you're trying to solve for y, you better get your y terms together. Terms, remember, are separated by plus signs and minus signs. And if you have terms, you could bring them across to the other side as long as you change their what? Sign. Okay? So 4xy, you're going to stay on the left, and you become the welcome wagon for the 2y that's coming over to your side. Of course, now it's a negative 2y, yes? The negative 1 stays on the right side, and he's now accepting, with open arms, 3x to the right side, which is now negative. See that? You're collecting like terms, just like you did in Algebra 1. Now, here's the thing. The two terms on the left both have y in them, but they're not like terms, are they? No. You cannot combine them. But you need a single representative of y. How do you do that? I like that better. Yeah. You want to factor out a y. Factor out a y, which is dividing it out. And you're left with 4x minus 2. Now you have y times blob. How do you solve for y? You divide both sides by 4x minus 2. So you end up with, I'm going to flip these terms, negative 3x minus 1 all over 4x minus 2. There's the inverse. So now we'll call it, what do we say? Do we wanted to call it h? Yeah, they gave us the name. So there it is, h of x. That's negative 3x minus 1 all over 4x minus 2. Now we're going to do a couple of things with these two things. All right, the algebra is the same, so get used to it. Let's come back up here. Let's find the domain of g. How do we find the domain of this function? Right, 4x plus 3 better not equal 0, right? I think we can do this in our head at this level. So if you set 4x plus 3 equals 0 and solve, you'll get x cannot equal what? Negative 3/4. Bring the 3 across, it becomes negative 3, divide by 4. So it's the set of all x such that x cannot equal negative 3/4. Let's figure out what the range of this is going to be. Remember, 2x minus 1 over 4x plus 3 was a transformation of your 1 over x function. Remember that? But we had to do long division first. So just knowing that, we know that the function 1 over x, or any of its transformations, the range is going to be every single y value except the y value where we have the what? Not the vertical, horizontal asymptote. We know that any transformation of 1 over x which is going to be linear function over linear function, is going to have every y value except the horizontal asymptote. We know how to find horizontal asymptotes, right? If we take the limit as x goes to infinity, because you look at the leading terms only, right? It's x to the first over x to the first. What is that ratio approaching? 2/4, right? Remember, it's leading coefficient over leading coefficient. That's your end behavior, which means that's what the y values are getting closer and closer to. So the range is going to be all the y values except the y value of the horizontal asymptote, which is 2/4 or 1/2. Now, let's see if we can answer questions about H from questions about G. I want to find the domain of H, and I want to find the range of H. If I know H is G's inverse, do I have the answers to those already without even looking at the function H?
Yes.
I do. What should the domain of H be? It should be the range of G. Good. So the domain of H is going to be the set of all x, such that x is not equal to what? 1/2. You want to use x's instead of y's. And the range of H should be the what of G? The domain. So it should be the set of all y's, such that y is not -3/4. Now, I think we have faith that that's going to be correct, but since we have the function G, we can what? We can verify. Let's come down here. If I find the domain of H algebraically, I know that 4x minus 2 shall not equal 0, right? It's the denominator. So that means 4x shall not equal 2, x shall not equal 2/4 or 1/2. Is that the same as above?
Yes.
Sure is. And the range of H, it's another linear function over another linear function, so this again is another transformation of 1 over x. So it's going to have every y value except the y value of the horizontal asymptote. Where's the horizontal asymptote on this one? -3/4, leading coefficient over leading coefficient. So it's the set of all y's such that y is not equal to -3/4. Is that what we got above? I sure hope so. It is. Awesome. So this makes a wonderful multiple choice question, doesn't it? If I ask you to find the range of h of x, which is the inverse of this, you don't have to like switch x and y and resolve and find h of x just to find its range, right? Because the range of h of x is the what of its inverse domain. And since the domain of this is everything except -3/4, that's going to be the range of its inverse. You save a lot of time. All right, now the last thing I want to talk about, because there's 2 minutes left, what should happen if we do h of g of x or g of h of x? You should get x. So let's try that. I'm going to try that real quickly here. I'm going to set it up at least. H of x is my outside function here, so that's going to be -3 parentheses minus 1 over 4 parentheses minus 2. And in those parentheses, I'm plugging g of x, which is 2x minus 1 over 4x plus 3, all over 2x minus 1 over 4x plus 3. And guess what we have set up for ourselves? A complex fraction. Did we spend any time earlier in the year deciding how to get rid of complex fractions? Yes. Why did we do it? For this. Essentially for this. Our miniature denominator is 4x plus 3. If you multiply by 4x plus 3 over 4x plus 3, look what's going to happen. When you distribute in the top, your 4x plus 3's divide out, and you're left with -3 times 2x minus 1, and then you're left with minus 1 times 4x plus 3 in the second term. In the bottom, when you distribute, you get 4 times 2x minus 1. Your 4x plus 3 is divide out again, and you're left with minus 2 times 4x plus 3. Okay, so that is the magical step. If you expand the entire top, you get -6x plus 3 minus 4x minus 3. In the bottom, you get 8x minus 4 minus 8x minus 6. And look what happens. Your 3's cancel, and you're left with 2x. Down here, your 8x's cancel, and you're left with, oh, did I miss a sign here in my haste? That should be a positive 6. I end up with 2. Those divide out, and we're left with x. All right, quiz tomorrow. We finished the notes. Have a great day. Don't forget noise is off tomorrow. Worksheet will be due tomorrow, too. Today. Today's noise is off. Worksheets due tomorrow. Yeah. Yeah, noise is off today. Worksheet due tomorrow. Be awesome always. This 6 weeks.